Okay, so let's start. Today I am going to tell you on the quantum phase transition by taking a model which is Bose Hubbard model, and that Bose Hubbard model is typically a lattice model. So you can take a 2D lattice, and after then you can uh, sit some bosons on the lattice point and see how the parameters are going to drives you into another phase. And in the quantum phase transition, the one uh, one possible reason of quantum phase transition is spontaneous symmetry breaking. And that symmetry breaking we can see from the Landau-Ginzburg theory by the expansion of free energy, and then we can have something, the phase transition due to the symmetry breaking, how the symmetry is broken for this model. And there are several models are there, but I am going to tell you on the specific model, which is the Bose Hubbard model. Technically this model is comes to the physicist's mind that for the fermionic system. And as the Fermi systems or the Fermi Hubbard model tells about the spins and their orientation and all that on the lattice point, and there is something Pauli exclusion principle will be there or will be applied. But for the sake of simplicity, then we can also put the bosons on the lattice point, and we easily find out all the physical phenomena that described by the spontaneous symmetry breaking, and we can have some phase transition, which is the quantum phase transition. So we can start the Bose Hubbard model. So the Hamiltonian of the model is basically minus t, which is the hopping parameter, and sum over I and j, which basically connects between the nearest neighbor lattice point, that is some bi dagger bj plus Hermitian conjugate. That means the hopping can goes from I point to j point, which is the nearest neighbor. So you can easily think of that j is I plus 1, this is the nearest neighbor. And then another term is mu, which is a chemical potential which controls the filling on the lattice point. So something occupation number ni is bi dagger bi, I will explain in a bit, plus u by 2 ni times ni minus 1. So these ni's are the number operator, and this is specifically I can see this. So this is bi dagger bi, and due to the boson, so we can write this occupation number density in terms of the creation and annihilation operator. So due to the pretty most good picture for the bosons that describe mathematically that the bi dagger bj, so I think it should be dagger, it's trivially delta ij. So if you take the fermions, then this commutation relation no longer be hold, then the anti-commutation will take part in this model, and obviously that the commutations of bi times a commutation of bi bj and Bi dagger Bj dagger is basically 0. So we can say this is a d-dimensional hypercubic lattice. This Hamiltonian can be represented in some sort of the generalized d-dimensional hypercubic lattice, and these sets of these uh, conditions are being implemented here, and this is very trivial thing. I wish you know all that. So, and now we can explain the Hamiltonian term by term. That this is the hopping, this is T. Hopping is generally, you can think of it's something the tunneling between the consecutive lattice point. So it tells us the story of the tunneling probability between two consecutive lattice point, and we specified a constraint that restricts some degrees of freedom, that the bosons cannot hop the next near or the next nearest neighbor, or the next to next nearest neighbor. We just specified and constrained the model to it can hop between the only the nearest neighbor. So this is our restriction, and which is implemented here in this angular bracket, which means it's a nearest neighbor index. And this chemical potential mu, we know something, the chemical potential which creates in the some grand canonical ensemble, we all know that if you add some particle, the energy cost is controlled by the chemical potential. And or if you just extract one particle from that point, and there is something called the excitation of hole, and if you put extra particle, then it's a excitation of the particle excitation. So that can be controlled by this parameter, which is the chemical potential. And this parameter controls the whole lattice, how they are to be filled by the bosons. So it controls the occupation number density. And this u by 2, which is the so by 2 is necessarily comes from the uh, combination, that if you have if the particle interacts between the other particle, and the interaction specifically between the two particles, then nc to the n choose 2 is the combination. So that's why this u by 2 is appeared in the coefficient, and n into n minus 1, and trivially from the n into n minus 1 by 2. But this thing, this u is something on-site repulsion. So if the lattice consists of a large number of particles, then how they will interact between them. So this is the main fact of the model. So technically, I think you have noticed already that this part is the off diagonal part. This part is off diagonal, and this part is a diagonal part. So we can easily think of how the phase transition will occur. So here you can see, if the symmetry is preserved, then there will be a conserved quantity. So in this model, the conserved quantity is the occupation number density. That's it. So in the case when the occupation number density is conserved, then the phase is known as the Mott-insulating phase, and that is the regime I will explain in a minute. And when this the conservation of the occupation number density is broken, then another phase will appear, that is a superfluid phase, and that should like something Bose-Einstein condensation. So it's a BEC regime. You cannot trace any kind of the number which is conserved. So there we can see the how the conservation principle is no longer holds for this model in the superfluid phase, and we can also discuss about the how the symmetry will be broken and all that. Okay, so I just erase this part. So here there is something, the quantum phase transition thing. So if you have a scale that's originates from here and it's something T by U, so U is our on-site interaction, and I think you should notice this, the Ni is Bi dagger Bi, and this part, if you normal ordered the operators, then you just have Bi dagger Bi and Bi dagger Bi, so it's look like, and this part is like, so it's a quadratic part and this is a quadric part, and it's something known as the ax square plus bx to the power 4, and for the value of a and b, which is positive and negative, and we get some spontaneous symmetry breaking here. So I will come to the problem on the theory a little bit later. So just it's some basic insight, how do you realize, and if you it's a normal order, and if you make the normal ordering, then I guess this u by 2 gets cancelled out due to the commutation relation. So the commutation relation allows us how we deal our free energy and all that. So okay, so it's in the quantum phase transition, how do I realize? So there is a two type of regime. It's something strong coupling regime, and this is something weak coupling regime. Coupling regime, and here maybe something, some critical point, or here we just analyze our critical theory. So here is something Tc over U, something critical hopping, this part, and in this section the strong coupling means the hopping rate is trivially very much smaller than the on-site interaction. So this is something T less than U, and the weak coupling regime means T is much greater than U. So here the hopping probability is much larger than the on-site interaction, and the on-site interaction holds the particle to live on that lattice point. So that's why we can think this kind of structure. And then and this Tc by U, this critical parameter, that depends on the chemical potential. So that means the mu. So it depends on mu, the chemical potential, and this is a quantum critical point. So you may termed as a QCP. It's a quantum critical point. So in this regime, where the strong coupling regime, that means the on-site interaction is much larger than the tunneling probability or the hopping strength, then we just think that if this is something a lattice, if you think of in the one-dimensional picture, so you just you can think of in the hypercubic space, but for sake of simplicity, just I uh, think or demonstrate it in the one-dimensional case and draw a schematic the one dimension. So if the n equal to 1, then the number conservation is hold that the occupation number density, then all lattice point consist of a one bosons, then this you can think of that all lattice point consists of one particle and one bosons. And so in the superfluid regime, where the weak coupling regime rather I say, where the hopping is much more larger than the on-site interaction, then if you make a surface plot over here in the kx and ky, then you just get a peak. So this is some occupation is being diverse. So basically in the momentum space, what we see that the accumulation of the bosons are be in the kx and ky equal to 0, and it flocks the bosons number. So that is the superfluid phase. So this phase is known as Mott-Insulator in the strong coupling regime. So it's Mott-Insulator, and this phase is known the superfluid. So SF and superfluid, and it is the critical point after. So before this critical point, it necessarily we hold the Mott-insulating phase, and beyond the critical point, we just get a superfluid phase. So due to the broken symmetry and the conservation does not hold the occupation number density, that no longer be conserved beyond the critical point. So this is it for understanding or the basic understanding of quantum phase transition. So now we are going to uh, think of one thing, that so how it look like, how the plot will looks properly. So I just erase the part to create some space to write further. So necessarily you can see. So I know, so when we have some Hamiltonian, and if it is diagonalized, then we have some energy eigenvalues. So as you see, here is something, the hopping term involves some off diagonal entries on the square lattice or the square matrix. And when the off diagonal term is involved or appeared, then we have to systematically diagonalize and extract the eigenvalues from setting an eigenbasis, and then we can have the whole range of the idea of the Hamiltonian. So before that, we want to do this in the trivial sector. So what is the trivial sector is here? So trivial sector is in the atomic limit. So what does the atomic limit is basically means that the system at the when the hopping is basically 0. So T over U is tends to 0. So it's a very small hopping probability of the hopping strength. So it's our atomic limit case. So in the atomic limit, our Hamiltonian can be written as the H0. So this part I just named it's H0, and maybe this part is named H1. This is an off diagonal thing, and H0 is the diagonal thing. And you can see the whole Hamiltonian is something H1 plus H0. It's a diagonal, and these are off diagonal. So this is it. So H0 is basically minus mu ni plus u by 2 ni minus 1. So if I take some Fock basis, the n basis, the number basis set, then we just find the energy is epsilon n is basically minus mu n plus, or maybe u by 2 n into n minus 1. So we obtain the ground state by minimizing this energy eigenvalue, and all obviously this n is belongs to the 0, 1, 2 and etc. So for obtaining the ground state, we have to minimize this epsilon, these eigenvalues, or maybe I just write it as the epsilon naught to specify it that the energy eigenvalues are obtained from the diagonal portion of the Hamiltonian. So this is it. So if I rearrange the number of bosons per site is the n, and if you just rearranging it, you can just think of u by 2 n times n minus 1 minus or plus 2 mu over u. So this is the one kind of rearranging our epsilon n. Not necessarily. So epsilon n. Okay. So I just erase it to write the all thing. So after minimizing all this thing, that epsilon naught n is minimized by the integer, minimized by the integer, which is maybe mu by u plus half. So as I just write down here to recall the portion, that minus mu n plus u by 2 times n into n minus 1, and n belongs to 0, 1, 2 and so on. So this is it. This is the structure. And if I plot that, I just minimize this epsilon naught in the atomic limit. So what we get, that this kind of minimization, and this value is tells us that the mu by u plus half, and this point is basically 1 plus 2 mu over u. And if you just plot here n, and the vertical axis are to be epsilon naught n, and which is this. Okay, so now if I just want to look about the occupation, how the occupation of the number density occupied on the lattice point in terms of mu, then if I just plot here, then this portion is n0 equal to 0, then n equal to something 1, then n equal to 2 and so on. So this part is n equal to 1, this part is n equal to 2, and this part is n equal to 3. So this 1, it's 2, and similarly it's the value takes it's 3. So it is something steer like structure which is being obtained from the energy values from the diagonal part of the Hamiltonian, and we just get this kind of a phase, that how the occupation number, how the particles are occupied on the lattice point, and in terms of mu by u, because mu is the controlling parameter and it controls how the particles or the bosons field of the lattice point. So that is the main reason. And now we can expect the phase diagram involving the hopping term, and then I just systematically uh, do all the calculation for this part. So we just expect the phase diagram will be looks like this. So we just find, if I plot here some hopping t by u and here mu over u, then we just see there is some lobes will be created, and systematically these lobes are getting smaller and smaller as the chemical potential rises, and this part, this lobe is unequal to 1, is the mi phase. And as you see, so it is the 0 point, and some critical hopping will be there. This is the n equal to 2 mi phase, and this n equal to 3, and so on. And beyond this boundary, but beyond the tip of the Mott lobe, we just encounter a phase which is superfluid phase, where the number is not conserved. So it kind of something BEC. So or the BEC attains at the superfluid regime. So now we can think that what will be here. So the critical analysis of the tip of the Mott lobe, and another analysis we can do, that if I uh, leaves this boundary mi, then we just step on the superfluid phase. But here, if I increase some chemical potential, then we just step on the superfluid phase, and then enters the another mi phase, which is the n equal to 2. So this point is very much important to analyze our critical theory, and this critical theory is basically originated from the Landau-Ginzburg theory. So by the expansion of the free energy, we always can do uh, this at its best part, and just our goal to analyze this part, obviously. So we want to find what is the critical hopping, what is the value of the critical hopping and all that. And then there is a trick, because it's a nonlinear model. So we can solve by the mean field theory. So taking a point, and I just systematically assumes that all the ambience or all the surroundings are typically same, and just doing the diagonalization with taking some Goodwiller ansatz, and then I just obtain the phase diagram. But I try to do this. Our goal is to quantum classical mapping for the Bose Hubbard model. So, in this lecture, that's our goal is to map the quantum and classical for the BH model. So the recipe is So the recipe, if I define the recipe to solve this point, that's you just have to find the partition function, and which from the canonical ensemble, and is a very uh, successful program to find the partition function. I think you don't have any doubt here. So trace is e to the power minus beta h. H is our Hamiltonian, and you can also write this up in the coherent state basis, that is the phi, that phi, so capital Phi e to the power minus beta h capital Phi. So we just sandwich this e to the power minus beta h part with phi's, capital Phi's, and you just get the partition function. And after that, you just know this capital Phi is the product state. So the product state over quantum states on the lattice sides is the product of all phi's, small phi's, is kind of a product state. So why we take the products is because we just going to jump into a path integral formalism. So path integral says or allows us to uh, move or to propagate from one point to another in the all possible paths. So we can just consider all possible choice of our propagation path and just take a product state. So we just integrate out to over the space, and all the possible paths are to be included here. And another part to move on to the path integral part, so we just uh, transform this sum convention summation for discrete. So it's something called for discrete case, and by the product of these bases we just move on to the continuous basis. So we just remove sums and replace with some integral notation. So for the continuous basis. Okay, so so in principle we can use any complete or over complete basis of Hilbert space. So we can use any set of complete and over complete basis of the Hilbert space. So this is it, and now just it's our recipe. So now the question maybe arise, so how the partition function can be treated in a trotter trick. So the trotter trick, so I can just find out the trotter trick. So trotter trick is basically just make some factor or make some cart, all the small carts between the whole time range and finding delta t, or you can use or coin the term of slicing. So basically trotter trick says in the whole range of the path integral you just time slice the all this part and just get a full basis set with the complete uh, or complete set of the basis. So this partition function can be written in terms of the thing, this phi is over phi is the phi e to the power minus of something delta t. It's something known as the imaginary time, and as our system is not the time dependent Hamiltonian, so we just introduce a time set, because in the path integral we have to write action and there always includes something canonical moment and all that. So imaginary time is very much important, that to write or structure the action or the in the path integral form. So here is the z part is there, delta t, and that imaginary time I slicing a little for the bases, and that allows us to write the whole path integral formalism uh, in a one line. So that's the trick. So it's known as the trotter trick. So just h, and you just slice that this time slicing method, and you just slice it's how many bases are you want to put here, and maybe for the n case, and minus delta t over h times h, and just phi. And in between here you just, for this complete basis I mentioned, so from here you can know this, it has profoundly find that this is something phi 1. So you may take this time slicing for the n times, you n times slice the time, the imaginary time, and so phi 1, or maybe here you may something squeeze like this, the 1 phi 2 over. So this makes something known as the complete basis, and this delta t or the delta tau is something beta over n. So this is our goal. So here is a beta is basically 1 over kT. So kb is the Boltzmann constant and the T is the temperature. So basically in the trotter trick or the time slicing part, we just easily think that the imaginary time is inversely proportional to the temperature. So as the quantum phase transition we want to study at the zero temperature or the absolute zero temperature, so just we introduce these times and all the temperatures for the case of to obtaining this partition function, and extract the all story from that beast Hamiltonian, and then we just find all the stories and extract all the information and just integrate out over the temperature or maybe the time, and we get our desired result. So that is the trick we just going to do. And now you may ask that a question, that what is the basis for the interacting bosons. So this is the one of the very good questions. So we want some basis. So I just erase because this board is too small, so I need to make some space to write the further calculation or maybe the further concept. So I think the calculation part will be teach in the next session. So maybe that's some question. What is the best basis for interacting bosons? So we want to be easy to evaluate that this kind of thing, that's the phi j is obviously capital phi j because it's the complete our basis set, and e to the power minus delta tau over h, that phi j plus 1. So basically it tells us the kernel of the system. So basically it's how it's evaluate or evolve with time, imaginary time, and also another thing will be there, that this is the part of the propagation amplitude. And also we can always bring the Hamiltonian into the form of the normal ring, which what I mean to say in the first few minutes. So Hubbard interaction action is basically something, some HU, maybe I coined the term, that is something U by 2 sum over Bi dagger Bi and Bi dagger Bi minus 1. So basically Ni times Ni minus 1. So it looks like this. So how do I normal order this operator and get like something quadric term in the interaction case? So that's I going to do, not going to calculate. So it's look like something U by 2 Bi dagger Bi minus U by 2 Bi dagger Bi. So as we know, for the case of normal ordering, all the dagger parts are try to move in this set on the left hand side of uh, the total uh, combination of the operator, because we want to know that the ground state will be annihilated very much easily if you uh, act the any state from the left hand side. So that's why we just want to move this Bi dagger to here and just this Bi there. So we know that the Bi dagger and Bi simply satisfy the commutation rule. So I easily know that Bi times Bi dagger is basically 1 plus Bi dagger Bi. So I just replace here. So U by 2 sum over Bi dagger Bi plus some U by 2 Bi dagger Bi, and this minus term, this U by 2 Bi dagger Bi. So it will get cancelled out. So simply from the normal ordering case, I just obtain the Hubbard interaction. If you just remove Hubbard interaction from here to, we can just simply write this U by 2 sum over I Bi dagger Bi. So it simply creates something called the phi-4 theory. So it's the very good thing. So our the Hubbard Hamiltonian after normal ordering, we can write this like this, minus T Ij Bi dagger Bj plus Hermitian conjugate so minus mu Bi dagger Bi plus U by 2 Bi dagger Bi. So it's our complete Hamiltonian, the Hubbard Hamiltonian, for the bosonic system after normal ordered form. So it's after normal ordered. So that's it. So the ideal solution, the basis of the eigenstate of the Einstein operator. So this is our best basis we can use in the non-interacting bosonic system. So that's it. So now we just dive into something like how it will be look or something else. So now it leads to some elements of a matrix form. So why? So I can choose this kind of basis. So I just, if I remove or erase this part, so now I can really assure you why this kind of annihilation bases are using best for deals with this kind of interacting bosonic system. So I just think of like, if I just expand in a bit, so I just write it approximately. It's something phi j 1 minus delta tau over h phi j plus 1. Sorry. So it leads to us to the matrix element, which is something phi j b dagger dot dot b and phi j plus 1. So we just operate here and then there, and it is being these dagger quantities operate there to annihilate the ground state. So if the phi is the eigenstate of B1, we can replace B by its eigenvalue. So that's the main goal, and we always know this phi j of B dagger is basically equal to B phi j of dagger. So bra of phi j on acted on B dagger and is equal to this annihilation operator, so ket phi j, the whole dagger. So this is the it. So we can indeed construct such a basis. So this operator consists of eigenvalues which annihilates the operators. It's known as the coherent state basis. So coherent state basis. So I just tells you why the coherent state basis is the best basis we can deal with to solve the interacting system, the interacting bosonic system, and here is the logic. So that's it. And now after that we just calculate all the coherent state systems and how the coherent state is operated by some operator, this creation and annihilation operator, and then we systematically uh, follow through all the recipes I made here. So then we calculate all the thing explicitly and see the results. So for the curiosity, you can just hold your curiosity and stay tuned for the next session. So I just calculate all the thing I just mentioned here in the recipe. So that's it.